All right, good morning. It's 9:40, so I will start sharp so we can have maybe some time for Q&A or just give more minutes back to your morning. And I'm Teresa Wu. I am very pleased to be here presenting here at IDEMIA. I think it's my first time actually as one of the main presenter. I've been here in IDEMIA before as a panelist, but this is my first time presenting, so I'm a bit nervous. I will have to say that someone actually, just before I walk in, give me a huge boost of imposter syndrome by saying it's kind of scary that this is the only post-quantum presentation in this conference. And then I said, yeah, and it's Teresa Wu presenting it. So, so I will say first disclosure, I am not a crypto expert. I have never studied quantum computing. I have a business and marketing background. And I got all the knowledge and training from my colleague, Olivier and Nora, that was helping me to better understand the quantum computing threat. And I got scared. And I feel like we, as identity professionals, should know about it and talk about it. And that's why we are doing this talk together. So I am definitely not the expert in the room, but we want to raise the concern of what can come. I think in the opening keynote and many other sessions, we talk about AI and the threat of how AI and the fake identity and synthetic identity can threaten our identity management ecosystem. And I think if you look a little bit further ahead, this other scary thing coming. And I'm hoping that with this, you can take away that we all should get ready now. AI is not mainstream, and I'm hoping the quantum threat will go mainstream, and we all, as a community, will start preparing for it. So, quantum threats, what's the deal? I don't believe I need to explain what quantum computing is in this room. I think more or less we have a good notion what that is, right? But the quantum computer becomes super efficient in solving specific problem. And you look at what's going on is the size of the key and the time to resolve, right? So what's happening is as the quantum computing is getting more efficient, the size of the key doesn't really matter at some point. That's the problem. So no matter how long your key is, it's not buying us any more time. That's I would say the major threat is the key won't matter. With the symmetric cryptography, we are still okay, but they can accelerate the search of the keys. So if you lengthen the key, yes, you're buying yourself more time, but as quantum computer gets smarter, get optimized, thanks to probably AI, we are just chasing the inevitable, right? And the asymmetric cryptography, that's where the things break. So, so this is the threat, and the timeline horizons. The Global Risk Institute did a survey, and they did a sort of asking different experts, what you think when a likelihood of a quantum computer can able to break an RSA 2084 keys in 24 hours. So what's the likelihood, and what's the timeline, what you think, and they categorize this in this table. So number of respondents saying when, and it's 30 years from now, 20 years from now, 15, 10, 5 years from now. So all that, we summarize it is basically, it's a flip of a coin. It's 50% expert thinks that there's a 50% chance. I think everybody just don't know, so it's uncertain at some point. It's just like the event horizon is 2030 to 2035. May I say, this event is only meeting, and Olivier highlighted to me when we're prepping, this is not a collective thing. It's not industry readiness thing. We just need one quantum computer to break the algorithm in 24 hours that's online, and that's it. That's when this happened. We only need one. As you know, many state nations has been investing in quantum computing, and it's on a quantum computing race to build the computing powers. On one of the presentations I did, someone asked me, do you really believe in this date? Do you think it's sooner or later? I believe more 2030 and maybe sooner. And I would say that anything after, I think we're just being complacently optimistic. So it's not that far away. So with that in mind, luckily we do have awesome government agencies has been looking on working towards raising preparation for it and looking at when we need to comply with quantum safe cryptography and when we're going to have to start applying it. So there is this timeline saying, well, we start preparing and inventory, prioritize our system. NIST will publish the post-quantum algorithm standard, and it's been this process of selecting. There's and so forth. There's ongoing work going on. NIST is doing a good job at it, not because they're in the room that I say that, but because they're doing a good job at it. So, and then here is starting, we're saying transitioning 2024. Should start. I don't know who in the room have been working on budget to plan for your quantum system transition for 2024. That's next year. So if you have budget cycle, maybe you want to put that in your budget. I don't know. I am in the room, just saying. And then this is the 2030 event horizons. I have to say that CISA did sponsor a study and have listed a list of what we call national critical functions. And one of them is provide identity management, associate trusted support services in one of the 55. They rated like different level of priority importance, but it's also been highlighted right after in the among the 55 that it's one of the top 3 critical enabler for PQC migration. And if you look at this chart here on the timeline, this is the event 2030, this is 2033, and actually start seeing that, well, you're gonna have to start looking at your firmware signing, your web browser, when you're gonna need starting to do in terms of your migrations. So what does it mean for identity management? So I take that global context. What does it mean? Well, how post-quantum will impact us? And I believe this is your slide. So
Thank you, Teresa. So you've seen quantum computer and a timeline. I'm probably here, you all believe that's fine. We've done RSA to ECC migration. This is one more cryptographic migration, not a big deal. Two main issues. The first one is who has finalized the RSA to ECC transition after 20 years? No one. It will be the first time in the history of cryptography that we need, on a timely manner, to change all algorithms. It has never been done on any algorithm in any security foundation. The second thing is that if you move from RSA to ECC, it's mostly to be able to protect a little better your systems. Here, quantum computer, you have to think of it a little bit like Ebola. When you have Ebola, your blood is flooding from everywhere in your body. If you look at a quantum computer, we are compromising the foundation of the security of the system. And for an identity solution, we are compromising user identity. I can fake whoever I want. I can destroy your identity. I can change it. You've seen AI. Okay, ChatGPT is there. You can fake impersonate. Same thing, but in all the IT organization, in all your identity management system. And the second is I can compromise all access management systems. I can compromise authorization. I can compromise authentication. I can introduce device. You don't even know there is a device. I can remove a device. So it's all your solution that is compromised. Now, the real question is, how do we protect against this quantum computer? And just to remember, we just need one SAS computer. For everyone to understand, you get an authority root certificate, send it to the quantum computer, and you get the authority key. And then you can reforge any root certificate. This is the powerness of this computer. How do we protect it? 3 steps. The first one is we have a quantum computer that is able to break RSA and ECC. Best way to protect it is to move away from the shooting area. Quantum computers are extremely good on some problems, but the problems that they don't know how to solve, they don't know how to solve. It is not a more powerful computer. It's a computer that works differently. And so if you're moving away from what they are able to do, then you are safe again. So for symmetric cryptography, we just increase the key length, should be okay. For the other one, we go to other cryptographic algorithms. You have them on the left side of this slide. Now, there is a problem that you see on the left side, is we used to have 1 or 2 for each function. Here you see a bunch of algorithms. In fact, we will need many more algorithms than previously. Some digital signatures are easy to sign, difficult to read. Others are easy to read, difficult to sign. They work differently. It's not plug and play. It's different grammar. The second problem you see is that sometimes, if you want to implement quantum-safe algorithm, you move away from what quantum computer does. So there's no question, everything that is on the left side is quantum-safe. The trouble is, you still have classic attack. You still have mathematicians. These are very young algorithms. They have never been used on the field. Maybe somebody will find a solution. You have one of them. So this is the official NIST list. I don't know how you beam. OK. You see the small bicycle? This is called bike algorithm. Last month, or 2 months ago, somebody found a mathematical solution. You can break it on a single PC. And this was a finalist. And that can happen next year for the one selected. So that's why the NIST not only has found the algorithms, but for each algorithm, there is a backup. A completely different backup. So if you find a solution to one, there is still a backup. And you see that there is a fourth one. Why? Because there is, for key exchange mechanism, there is no backup. So they are looking for a backup. Which means that not only we have a more complex grammar, but we need to be able to switch to a backup if somebody finds a solution. And just to envision, if somebody finds a solution, let's say, to Falcon algorithm and solve it in 1 day on a PC, you have less than a month to migrate all your systems. Otherwise, you will get an attack. So it's not only you need to migrate, but you need to migrate at a speed that nobody has ever done on cryptography. Once we have done that, then we need to redesign all protocols. And you see the 4 layers. We need to redesign the communication protocol, TLS, VPN, HTTPS. Then we need to redesign the cryptographic infrastructure, public key infrastructure, certificates, digital signature. And then the top layer, the end-to-end architecture for authorization and authentication. The heart of all identity solutions need to be rethought. Understood how this impacts the architecture, both on security, but also on performance. Because these certificates are much bigger. Performance, you need 4 or 5 times more computing power. And last, you need to revisit the user identification means. All your ID documents will need to be changed. All your Ubico keys will need to be changed. Your PIF cards will need to be changed. And that's not done in a flip of a corner. And everything needs to move forward in standardization to meet NSA and CISA timeline. So 2025, in 2 years. In 2 years, we are supposed to have finalized everything. Difficult to figure out.
Well, but you said that we always do like 1 year late, it's okay.
Yeah, so 26. That's not the worst. Because so far, we are in the simple and easy part. The worst is to come, which is crypto agility. Crypto agility is a very new concept. Not at all the one you were expecting previously. It's a completely new concept. These algorithms are very new. We know from RSA perspective, when RSA was first launched, there was 1 patch per month almost. Patch all the time, because we were discovering how to implement them, discovering new attacks, discovering new ways to break it. So for these quantum-safe algorithms, we are going to have to apply patches in a very timely manner. Most probably, open source solution will have many 0 days. So you won't want to use open source solutions because they were full of vulnerabilities not yet discovered. Now, the second thing is that some algorithm, as I said, can be solved. So you need to switch to a backup algorithm. And last, for the first time in history, the standards, actually we keep on evolving in order to change the cryptography or to apply the patches and to learn on how we use that. So we are entering a world of simplicity, and we're entering in a new world of complexity, multiplicity, and dynamic change. So try to picture that. You have to dynamically change all your PIV cards on the field in order to maintain them up to date. Nobody has ever done that. The first certification step is make sure you can't change anything. So with crypto agility, we are violating rule number 1 of certification, which is you don't change a crypto. Here, you have to change a crypto to be certified. So we are taking the house, putting it upside down, and changing the foundations. How do we prepare for that? As I said, 2024, NIST will finalize the standardization of the first set of algorithms. The second step will be selected in 2024, standardized in 2026. Protocol, IETF, and others, 2028. So if we wait until all the standards are set, you're sure to be killed by quantum computer. You are out of the calendar. The issue we have is that the quantum computer, the people working on quantum computer are working too fast. And actually, they are keeping on their promises. If you look at some of the vendors' trajectories, they are every year delivering what they promised. So most probably, they will deliver the quantum computer ready for weapon attack in 2030-35. Okay? Most probably could be available for North America, Europe, China, and maybe other people finding a way to just have access to a single quantum computer in a SaaS mode. That's the bad news. The good news is crypto agility. Crypto agility is very complex to understand, but it also means that it will always change. So it means that you can prepare now. Thanks to crypto agility, you will be able to adjust later, which is what we actually do. Try to understand and anticipate and start working on the architectural solutions, try to understand the impact, try to do proof of concept to start putting on roadmap, start developing the solution that we call quantum ready. Maybe not on the standards, but with crypto agility, we'll evolve to the standards because these standards will be evolving. So the key feature is this ability to evolve all the time. And these preparations need to happen in 2 layers. The first one is in the cloud, on a digital layer. Where am I using the cryptography? What is the impact on my identity solution? Question 1. How do I reconfigure it to meet the performance, to meet the security? What does it mean? What are the impact on my security framework? The second is, what are the new services required? I will require services to help my customer migrate. I need to develop them now because they will need it for migration. I need services to understand if I apply properly the patches everywhere and the current status of all my devices and all my systems in data centers. I need services to move, to switch in case of major vulnerability, to respond in a timely manner to a major threat. And the last thing is, what does it mean, crypto agility? Let's take an example of Linux operating system. If you change cryptography all the time, most probably you will have to recompile, retest, and others, and regenerate Linux operating system all the time. What would be the right architecture to separate the cryptographic agility from the rest of the system and maintain some stability on the main system? And all that can be worked out without having the standards. You just need to work on the right families, but you don't need to wait for the standards for that. The second step is the physical world. If I take smart meters, 20 years lifetime. So smart meters deployed today will be there in 20 years. They are all quantum vulnerable. So it means that with a quantum computer, I can organize and orchestrate a complete blackout in the US. Or I can change indexes and change the load balancing of the core network of electricity. Nobody wants that. And the security agencies will not allow for it. So they will need to migrate before 2030. No matter how difficult it is, it will be forced. And those companies who will have the quantum readiness, the quantum ready product, will be the one that will be ready to meet the quantum threat. The other one will wait and will be lagging behind. What it means to prepare the physical world. how can I make sure that the device I put on the field will be able to migrate when it's mandatory? I take a single example, eSIMs. Everybody's using an eSIM. Today, no eSIM is crypto-agile on the field. Why? It's because GSMA certification says...
Olivier, explain. Do you know anyone what the eSIM is? Right, the one that goes to your mobile phones for connectivity? Okay.
So the eSIM, in most connected devices that are using the mobile network, you have a component which is equivalent of a SIM, but that you can remotely update. This component today, if you want it to be certified for telecom operators, the first requirement is you can't change cryptography. So you can be sure that all certified components that are soldered in smart meters, in your smartphone, in your automotive, are by certification not crypto-agile. So the first step is how do I change that to deploy equipment that will be able to be updated by software update and not be forced to replace everything. Biometric readers, access control systems. All these type of things today are not crypto-agile. So existing one will need to be replaced at a certain time. New ones, if you are not quantum ready, you're putting more oil in the fire. The second question is, how do I manage crypto-agility on all the assets distributed? Think of a company with all the badges, all the access control systems, all the data centers, all the system authorizing, remote access, VPN and everything. All that needs to be crypto-agile in an orchestrated way. Same thing. We've never done that, and that's typically a very fundamental question that needs to be addressed now. So if I summarize all what we've seen, you've seen AI at the beginning of the conference. Quantum computer, I will not be able to show it to you. What if you visit labs, you will be able to see is quantum computer already able to break short keys, and they are progressing. Quantum computer, AI, brings impossibility to know what is true, what is not true. Quantum computer enters everywhere in the system. The whole system is vulnerable. Your attack surface is now everything. The issue is, to migrate to quantum safe world, it has a tremendous impact on your system. And our experience is that when you have not started working on proof of concepts on these two steps, it's very difficult to imagine the difficulties you will have when we have never faced them in the past. And timing, all security agencies, we showed you the US, but Europe is the same, India is the same, Japan is the same. They are really afraid of a quantum computer being available for malicious purposes starting 2030. Thank you very much. Yes?
Spoke of communication protocol development in the light of quantum computing algorithms. Could you shed some light on the difference in the math behind the algo for, say, a diffie-Hellman modular arithmetic-based or elliptical-curve-based algo versus a quantum computing algo that would need for the protocol basis to change, the handshake to change?
Okay. So typically for communication.
Olivier,
yeah. Yes. So the question was to take an example of the communication layers, how quantum same algorithm would apply on establishing, let's say, a TLS communication, which usually today is done by an algorithm which is called Diffie-Hellman. And that actually illustrates the complexity. When you establish a TLS, you want to go to your banking website and do an HTTS. What is happening is that first you exchange certificates. And this exchange of public keys, of public certificates, allows you to do several things at the same time. First, you are sure, if you log onto a banking account, that it's your bank. So this exchange, in one single operation, ensures that you are with the right, authenticates the sender and the receiver. And second, it also at the same time builds up a shared secret, so something that only the two know, that will be then used for fast communication using symmetric cryptography. Okay? So quantum computer, symmetric cryptography is not an issue. You will exchange the keys, that's fine. The question is, how do I authenticate both the sender and the receiver? And how do I exchange a shared secret? And that's where it's different. In fact, in quantum computer, you have to use two algorithms. One is checking the signature of the certificate. So you have to exchange certificate and check the signature. And obviously, if I look at the complexity, if I do it with a smart card, the smart card is not powerful. I want to have a signature that is easy to check, and I don't care if it's difficult to sign. In a data center to data center, it might not be the same design choice. And the second thing is then I need to do what is called a key exchange mechanism. So I generate a random number, a secret, and I send it to my user. So that's, in fact, where you used to have a single operation. Now you have two with different type of algorithm. And to add to complexity, given the fact that we don't know really today, we don't have enough lessons learned on the new algorithm, most securities agencies are saying, okay, not only you're using the new algorithms, but you are also adding a layer of the previous one. So in fact, in all the implementation today are called hybrid, which is I use a new one, but for security reason, I add a new one. So just to give you an example, on the communication between a card and a reader, the timing, we are going from 300 milliseconds to 7 seconds. That's roughly what we're speaking about. Okay? So people are working on the hardware acceleration of the things. You have an overhead of 1 times 2 times 3. Now think in the data center. Go in the data center and remember the number of operations. We are speaking about times 2 and times 3 on the timing, on the performance on the CPU. You're communicating, we're multiplying the communication by 2 or 3. I mean, this is the amount of complexity and stress that the new algorithms are going to bring to the new system. I don't know if I answered your question. Okay.
Chris?
Actually, that's a perfect segue. My follow-up on the timing. So, last 20 or 30 years, PKI has greatly benefited from hardware acceleration. But going to a software-based crypto agile system that's not available. So I was kind of curious how your strategy, thinking in terms of the business model, because everything is going to be much slower.
I never said it will not be hardware accelerated. We're working on hardware acceleration that is compatible with all the families.
But if the fifth or sixth family has to be introduced because there's
We want, I mean, it's complex enough, so we are going step by step. Today, the industry is working on NIST algorithms. They all have a backup. So that's why I would advise to always work with 2 families to get the backup. Once you work with 2 with a backup, the probability that researchers find a major vulnerabilities in the 2 families, here we are really, really far away. So the industry consensus is that if you're able to implement 2 families, by the way, the second level of family is much bigger than the first one, but if you're able to work on this set of assumptions, you're probably safe for 30, 40 years. If you just work on lattice, 1 family, here you are taking a major risk on your solutions. Now, in terms of performance, everybody is working on hardware acceleration. Our specialty is on secure elements. So we have hardware accelerated secure elements that are going to be released, and we're working on acceleration that is able to accelerate everything. Now, on data center, all the data center providers are doing the same thing. At the same time, when you do architecture, when I was speaking about architecture, you might want in some places to move from asymmetric to symmetric. There are places where it was easier to use asymmetric and you can move, reduce the attack surface and reduce the places where you really need the overhead. Yes?
Andy Wright from this. I will first of all note that you can expect to see some draft standards from this for those 4 selected algorithms very soon. Keep an eye out this summer for that. I will say you don't really describe them as backup algorithms. I mean, we're very confident in those in what we've selected. But as you noted, different post-quantum algorithms have different performance and size characteristics, and so they're likely to be more suitable for some environments and some use cases than others. But I'm really glad to see you doing this work, because if you think about one of the last major transitions that we did in crypto, going from SHA-1 to SHA-2, just a simple hash function migration, that took 10, 15 years basically. And this is going to be a much more difficult migration. There's a lot of attention going on right now with things like TLS, but I think that those kinds of use cases, the migration to quantum-resistant crypto is going to be a lot easier than some of the use cases I see here with things like smart cards and IDO tokens. For things, the keys and signature sizes for these can be much much bigger, talking on the order of sometimes 10 times bigger. So thinking about how that's going to impact your APIs, how that's going to impact your communication protocols, how that's going to impact just the hardware that you use, is those things that are going to be really important. Because I think that's also going to need to feed into the standards changes that are going to happen at the protocol and application levels over the next few years. So thank you for doing this work.
If I may just add one more complexity layer, we are currently doing proof of concept with software editors on the application layer. And on this one, the impact is also tremendous. And in particular, the crypto agility, the fact to apply patches in a synchronous way is more. And so we really advise not to just stay at the protocol level, but there is a need to anticipate right now on the software editor level, because otherwise it takes 2 to 3 years more.
All right, so we're almost out of time. Just raise your hand. Who thinks are you ready for post-quantum? Anybody want to raise their hand? No. Thought so. I would say a takeaway. Thank you for coming. I would say that how to get ready, it's going to take a village. It's work with POC. Start doing pilot levels. Like start looking, even on the paper level, start looking. Right? If there is a disaster, everybody have a system outage recovery plan, right? In your organization. So start looking at, probably you're gonna need to draft a prevention, like a readiness plan, but also a recovery plan. Start planning, may not be, and then looking at start looking at concrete project to do POCs. This is what we have been reaching out to different companies to look at actual practical use cases to do POCs. It's the only way we can learn and take lessons learned and reapply and get feedback when standard comes out to give practical implementable feedback back to NIST to drive the standard. This is gonna take a whole village to do it. And you guys are in the forefront because you are identity professional, architect, product manager. This should be in your timeline and this should be in visibility. So thank you for coming and hope that you guys enjoyed this presentation.